Create an example of a sequence which is bounded but does not converge. Okay. So we don't want convergence, but we do want bounded. So maybe we could imagine some bounds and try and visualize our sequence. Now, we can't have the sequence increasing, because eventually we're going to run out of space and we'll have to slowly settle down towards some limit. The same reason we can't have the sequence be decreasing. Even if it's, bouncing around for the first little bit, if eventually it starts increasing and consistently increases, you're going to have to settle down to a limit. And eventually the values will all congregate together towards one of our upper or lower bounds. So, we can't have the sequence eventually just all head in the same direction. Well, what does that look like? Well, if you're not all heading up or you're all heading down, then you must be going up and then down, up and then down, up and then down. And the sequence should be bouncing around. Now, if we imagine them going up and down, we might run into this sort of situation where they're coming closer together. Maybe there's a limit somewhere in the middle between our bounds. Well, we don't want that either. So what we should try and do is come up with a sequence that sort of stays apart from itself. And a really, really easy way to do that would be just alternate values. Pick two values and say, well, my sequence can only have these two values. Maybe 3 and 2. And if all the terms in my sequence only have values of 3 and 2, then of course it's bounded. Pick a lower bound of 1 and an upper bound of 4 if you want to be really, really want to stick with the integers. But if one term is 3 and the next one's 2 and the next one's 3 and the next one's 2, you'll notice they're not getting closer together. They're staying a respectful distance apart. They're not increasing eventually. They're not decreasing. They're staying within this bound. And as we head further to the right, the function just keeps bouncing back and forth on its merry way, never settling down. Okay? When we visualize things, this can really help us sort things out. So we could say, for example, sequence 2, 3, 2, 3, 2, 3. I think they get it by this point. Is bounded, but doesn't converge. Yeah, that's a great example. Now, if you're the sort of person who says, well, that's great, but that's not really a formula, I would point out you could make like a piecewise formula. But for people who insist on, that's not a good enough sequence, well, yes, it is a good enough sequence, but maybe you might be a little more satisfied with something like this. an is negative 1 to the n. Okay, what's this going to look like? First it's negative 1. Then it's 1, then it's negative 1, then it's 1, then it's negative 1. It has this same bouncing back and forth, up and down behavior, but it's clearly bounded. Okay? So that's another good example as well. But I like the just pick two numbers and alternate between them. And it doesn't have to be two numbers. If you wanted your sequence to go 2, 3, 4, 2, 3, 4, 2, 3, 4, that's also not going to converge. The values don't settle down. They don't get closer. And it is bounded. Okay? Lower bound of 2, upper bound of 4. Okay? That would work as well. So there's lots of options, but what's important is that we reason our way through it and we say, all right, visually, what am I looking for? Okay? Things like the monotone convergence theorem force me to have to avoid certain options, and that leads us to this idea of bouncing back and forth, up and down. Okay? So there we go. Actually, it's a couple sequences that are bounded but do not converge.